Hi, I'm Warren Powell. Welcome to part two of Universal Modeling Framework for Sequential Decisions, Bridging Machine Learning, and Stochastic Optimization. So I'm going to start by talking about sequential decision problems. This is my wallpaper of all my activities. In part one, we took a look at all these decisions. Now, every one of these boxes poses a question. We're answering the question requires a decision. Now, after you make the decision, this is the information that comes in that was relevant to the decision that you made. Let me go back and do that again. So put your eye on any one box. We're posing a question. I have to make a decision, and then information arrives after the decision was made. Now, most of the settings, decisions are made over time. We have decisions, then new information arrives, and another decision. Information that arrives after a decision is made is not known when we made the decision. So examples, inventory management, I may place an inventory ordering decision. Maybe it arrives right away or well into the future. Then I observe the demands, and this will repeat over and over again. My startup optimal dynamics, we have the blue circles, those are drivers. The red squares are loads. I'm assigning drivers to loads. And then after I make the assignment, more loads get called in. And this evolves over time. It's a very high dimensional problem. Testing new vaccines, I may have to decide what dosage and which people to administer the vaccine to. And after I make these decisions, I see how they react. I see which people are willing to get the vaccine. Financial trading, buying and selling assets over time as prices are changing. Okay, now let's talk about how to model this with the Universal Modeling Framework. So the biggest challenge we have when making decisions under uncertainty is modeling. Now, when we have deterministic optimization problems or machine learning, everyone knows how to write out their problem mathematically. It's a very mature field. There's books on how to do this, especially for deterministic optimization. But once we get to sequential decisions, we lack a standard modeling framework. So this is my jungle of stochastic optimization. Every one of these terms describes a community. Behind every one is a book or maybe a whole series of books. Now, these are each different communities. This isn't like optimization or statistics where we have a lot of books on the same topic. These have 8 fundamentally different notational systems. The books don't agree on how to write down the objective function, how to express the problem. It's really quite a mess. So here it is in one PowerPoint slide is the Universal Modeling Framework. At any one point in time, I have data. So ST captures what I know or believe. It can be uncertain. Then I make a decision after that new information arrives, as I illustrated before. Now, every time I make a decision, there'll be some performance metric that depends on information in the state variable, as well as the decision. Now, decisions are going to be made with some method. I'm going to call it a policy. This is a function which we design later. Now, this is the major point of departure from all of those books on stochastic optimization because all of them have a method. They come to you maybe more than one method. But here, I'm just going to plug in a function and say we will get to it later. And that's a really key step. Now, whatever function I use, I'm going to get a decision. So give me the state and the decision. Now tell me the new information arrives as I step forward in time. And I have some way to say, here's the updated state variable. Now, of course, at the end of the day, we still want to have a goal of coming up with the best policy to maximize or minimize some performance metric. Now, I like to list all of these elements in these five categories. These 5 elements, once you've got it filled in, can describe any of the problems on the right-hand side, any sequential decision problem, and any of the problems in any of these books. This is truly a universal modeling framework. Now, there's also uncertainty. So I've come up with 12 classes of uncertainty from the perspective of a model. It has nothing to do with any application. So if you have a particular problem domain, you have to go down these 12 classes and say, does each one of these classes apply to my problem? If you have a complex problem like a supply chain or energy system or health, I'm pretty sure that all 12 classes will apply. But let's say you have a problem like playing chess. The only uncertainty is what the opponent is going to do, and so of the 12 classes, only one of these would be active for that. Now, uncertainty also comes in a number of different flavors, and we have to remember it's not just something uncertain or stochastic. Uncertainty arises with all kinds of different behaviors. It can be high frequency noise, low. It can be have bursts. You can have shifts. You can have black swan events. You can have spikes. Now let's talk about objective functions. In deterministic optimization, we generally assume that we have some well-defined objective function I'm trying to maximize or minimize. In sequential decision problems, I can have cumulative rewards where I'm optimizing the sum of the rewards over time. I can have a final reward where I do a bunch of experiments, but I only care about the final design at the end of the budget for doing experiments. And then there's also this element of risk, and I could speak at length on this, but I'm going to let that pass, just acknowledging that risk is generally an issue whenever we're dealing with uncertainty, and that is not going to cause us any problems. Now, each of these, we are still optimizing over policies. That has not changed. Okay, so let's start talking about the objective function, and I want to start with this S0. This is our initial state, and this is often overlooked. The initial state might be physical states like initial inventories, the location of warehouses, or the layout of a manufacturing system. Or it can be how much cash you have on hand. I is other information. It could be parameters. It could be what the weather's doing. It could be state of tariffs at this point in time. And B is the beliefs. This is where I have elements that I simply don't know perfectly, but I may have a belief either based on frequency statistics or maybe a Bayesian prior. Now, this is the state of the world. There are people who really spend their lives trying to figure out what is the state of the world. So knowing the state of the world is a big deal, and often I find that the modeling doesn't really give that enough attention. Now, we want to come up with the best policy. Coming up with the best policy means coming up with the right functional form. Maybe it's a simple rule or a linear function or a neural network. Could be a linear or integer, nonlinear or integer programming problem. And then often, most of the time, there's tunable parameters. And I have to figure out how to tune the parameters. There'll be some various methods for doing this. Now, evaluating the objective function, there's very simple problems like very simple inventory problems where I can do this theoretically and say, oh, here's an optimal policy. Much more often, I'm building simulators, and I'm using the simulator to evaluate and tune and test the different policies. But it's actually the fact that most of the time, the vast majority of time, we're really just evaluating in the real world. We just put it into production, and then we have to see how well it works. And sometimes that really is the only reason. Sometimes, often we're doing it just because we don't have the time to build a simulator. Now, when we evaluate policies, it's not just which policy works best in a one-dimensional way. Here I've got about 6 different dimensions: computational speed, transparency, flexibility is very important, methodological complexity, how hard it is to write it up, data requirements. Identifying the best policy is sort of a complicated, messy step. And, we may say, oh, well, this is a better policy, but if it looks complicated and you're not sure you can get it working, that may not be something that I want to run the risk in. So the idea of optimal policies is generally a myth. We're trying to work with good policies that work well and are robust. Now, let's take a look at our very classical math programming framework that I've been using up to now. And this is a very powerful framework. So it gets a lot of attention from Danzig, who came up with the simplex algorithm to solve this. But even Danzig would make the point that this framework allows him how to think about problems. And he always recognized the power of this. And it is very powerful. It starts off by saying, well, you have to create these decision variables. You have to have an objective function. And you have to have constraints that in some way tell us what are the valid decisions. But there's a lot missing from this. So this is what my universal framework handles. It still has a list of 5 elements. It's much richer. I can deal with beliefs. I can deal with evolution over time. I can deal with new information. Now, the math programming framework has the characteristic that we're optimizing over X. The universal modeling framework optimizes over policies. These are functions. So this is, again, a key difference from classical math programming. Math programming is focused over X. When we took math programming and said, okay, how do we deal with uncertainty? People have gone down certain paths. What we have to understand is once you go into the world of sequential decisions, which are all stochastic, you have to shift gears from saying not what is the best decision, but what is the best policy. Now, where is math programming? It's in the policy. So at some point, I am going to have to make decisions. That's where still enters the modeling process. Okay, so I'm going to close part 2 with a new question that I started to look at, which is what is a decision? Now, if you go to any book on deterministic optimization, a decision is X. If you go to any book on stochastic optimization, it might be X or it might be action A or control U, but these are always standard variables. Let me tell you what none of these books do. None of them actually define a decision. They just assume that you know what X is. But if you're going to model a real problem from the beginning, you've got to be able to say in English what it is before you can give it math notation. Now, what is a decision? So I did some research, and this is my favorite list of my gallery of 8 great names that have made fundamental contributions in the arena of making decisions, and it goes back 2,000 years. Not one of them actually offers a definition of a decision. They all offer insights or algorithms how to make decisions. Now, what is a decision? So Princeton, Daniel Kahneman is a Princeton psychologist, Nobel Prize in economics, 500,000 citations, one of the great thinkers in terms of how people make decisions, never actually offers a definition of a decision. So there's a book, Handbook of Decision Analysis, in its 2nd edition, and it quotes Ron Howard, well known in operations research community, in 1966. He said, offered an explicit definition: a decision is an irrevocable allocation of resources. So this handbook quotes that and says, okay, that's our definition of a decision. Now, the book by David Skinner, this is a wonderful book, elegantly prepared. In its 3rd edition, offers the definition: a decision is a conscious course of action and allocation of resources to achieve a stated set of objectives. I'm sorry, I'm going to go on record saying I disagree. So my formal definition is an endogenously controllable information class. So need a little bit of explanation there. So what do we mean by an information class? Well, for this context, I'm going to describe 3 classes of information. There's the state variable, that's whatever we know. It's what we have or believe. It can be estimates of unknown quantities. Now, once you take what you know, and people can have long discussions about what are the different types of knowledge, but I'm just going to say, okay, whatever it is that we know, anything that you can store in a computer, a decision is where you create information. I have a set of choices and I make a choice, and then I move forward. So I have made the decision. I'm actually making information there. And then the exogenous information is the information that I don't have any control over. It comes to me from the outside world. So we have what we know, we have what we make, and then we have what just arrives to us as our 3 major classes of information. So, okay, normally I don't use my formal definition. I'll just say, okay, something we control. Now, much more usefully, I've come up with 6 types of decisions. Now, a math programming package like Gurobi will really focus on type 1. Type 1 is the vast array, the massive majority of math programming problems are for managing physical and financial resources. And there's a endless array of these problems. But also very familiar to the optimization community is tuning parameters. That's a well-known, goes back to the 1950s, tuning parameters using derivative-free or derivative-based logic. Now, a subtle piece of information, a subtle decision for the math programming community is choosing functions. And here there's different types of functions, but I'm going to talk specifically about the model. So if I'm using a linear program, the linear programming model is a decision. And if different people were to model the same problem, if it's a complex problem, they're going to make different choices. And they're going to have trade-offs in terms of level of detail and the robustness and the computational speed. So I think it's useful to have this list of these 6 types of decisions because it helps you look at a problem and say, oh, well, that's a decision. Okay, this brings part 2 to an end. I hope you continue on to watching part 3.